All right, welcome to CS 161 lecture number 15. It is actually lecture 15 this time. We made sure to check. But yeah, we do have some announcements before we begin. They're pretty much the same as yesterday. Homework 5 was released yesterday and it's due next Monday. If you want to talk about your design with a TA or with one of the instructors, just depending on what time you signed up, we have 15-minute time slots available throughout this week. So you can go ahead and sign up on a link. It's available on Piazza, and then you'll receive a Zoom link to do your design review on. Um, this calendar link, there's nothing there. And please only sign up for one. We only have limited availability and limited number of TAs, so don't sign up for multiple. That's just not a nice thing to do. We released Project One write-up grades, so most people got 100%. You probably don't need to be worried about the grade you got on it. But if you do notice that we didn't give points where we were supposed to, feel free to submit a regrade request. The design doc draft is due tomorrow, so definitely keep working on it and get started if you haven't already. And the optional lab is released and is due several eons from now. It's due at the end of the semester. We don't really care about it that much because remember that the homework can replace your lab grade, and most people tend to get 100% on the homeworks. So last time we talked about XSS, where websites use untrusted content from users and they use it as HTML data, which is treated as control data. So they can go ahead and just replace this snippet of text here with a script tag. And maybe this script inside is malicious and sends your cookies to the malicious server. There are two main types of XSS: stored XSS, where the payload is stored in the server. Maybe it's a comment or a Facebook page or something, and reflected XSS. So this is something like a search page where it says you searched for cookies and it says 1,000 results for cookies. We can do the same thing with JavaScript there, where we send the XSS payload and the server reflects it back to us, and it gets printed in the HTML and runs as a script. To defend against this, we want to use HTML sanitization. So these have special data sequences of characters that are treated as the character and only as data, not as control. So instead of using something like a less than symbol, we use ampersand LT in order to tell the browser this is just a less than symbol. It should not be treated as control whatsoever. And there's also a sort of defense in depth measure called the content security policy. This just is additional instructions to the browser to only use certain resources and only use them in certain ways. This is enforced by the browser, and not all browsers implement it. So it's definitely not bulletproof, but it's good as a defense in depth measure. We also went into UI attacks a little bit. So clickjacking is when you trick the victim into clicking on something that's from the attacker when they meant to click on something else. The browser tends to assume that the user trusts or the user knows what they're doing, so we can exploit this trusted path between the user and the browser. This can be anything from fake download buttons to invisible iframes to temporal attacks, where we replace the item that's on the screen the split second before they click on it, and a cursor jacking, where we actually create a fake cursor that is more visible than the real cursor. To defend, we can enforce either visual or temporal integrity, ask the user for confirmation, just make sure that they know what they're doing, and use frame busting for the iframe attacks, where we just instruct the browser not to ever let this website be embedded. We also talked about phishing attacks, which is where the attacker sets up a fake website and tries to trick the user into giving them their personal information. Really, the main takeaway is you don't want to blame the users for this. It's hard to detect phishing, and there are always ways to make phishing even better. So it's definitely a bit of an arms race. The best defense here is two-factor authentication, or 2FA, where the user has to provide two different ways of proving their identity. So generally, it's something you know, something you own, or something you are, and you want two out of those three, or maybe all three. These defend against attacks where, say, the attacker only stole the passwords. Some of them are vulnerable to relay attacks or social engineering attacks. And we talked about a couple examples, such as authentication tokens, which rely on cryptography, or security keys, which rely on even more cryptography, except it's embedded in a processor inside a physical key thing. There's a good question in chat. What if you wanted to write literally this sequence ampersand LT semicolon. And Nicholas is exactly right. You would have ampersand AMP semicolon. That is the sequence to represent an ampersand, and then the L and then the T. And I think there's a sequence for a semicolon as well, but I don't remember exactly. It could also just be, yeah. I'll just type it in chat really quickly. Something like that. That might work, it might not. And you can't see it if you're watching the recording, but it's okay. All right, so we're going to talk about SQL injection today. We're going to sort of generalize that to command injection. Before we go into any of that, we'll also talk about the structure of most modern web services. And then at the end, we have a brief discussion about CAPTCHAs and some ways to get around them. So SQL injection. Again, here is the top 25. I don't know why we say top 25, because there are definitely only 17 of these here. But the top 17 vulnerabilities that exist in any piece of code that have been written anywhere. And today we'll see we're addressing number 6, which is SQL injection. So before we can talk about SQL injection, we need to talk about what is SQL and why are we using SQL? What place does it have in modern web services? So the overarching thing for a lot of services is that they need to store data. For example, a website might need to store accounts for different users. They might need to store comments. Say on YouTube, you write your comment, that has to be stored somewhere. Maybe on a shopping website, someone needs to store the prices of the items and so on and so forth. The HTTP server is only really there to handle the HTTP requests. It doesn't really have a built-in mechanism of storing this data. So the way most services work is that we actually have 3 parts. We have the client here, that's your web browser, and that handles the parsing and the display of your website. There's the web server, so this processes the requests and it handles, say, the server-side logic. Maybe it looks up a password and hashes it, or hashes a password. And then we have a database server, which is actually there to store the data. So if you've used something like MySQL or Postgres or SQL Server or MongoDB, which is a newer technology that's emerging, those are the database servers that store persistent data. We have 2 different protocols in this diagram here. Between the client and the server, remember that these speak HTTP. So this is the protocol we were learning about, I think it was on Wednesday. And between the web server and the database server, usually we're going to use SQL. For the purposes of this class, you can assume that we're using SQL, but for something like MongoDB, you're using a different interface, but just pretend we're using SQL for now. The full set of steps that we need to go through is step 1, the client requests the page. So I want to go to cs161.org. This gets sent to the web server as a GET request. The web server receives this request and sees, oh, this web server wants cs161.org, or this request wants cs161.org. And maybe on this page, there's a list of, I don't know, lectures that are stored in a database. So now the web server has to go, okay, let me look up what the list of lectures is most recently. The database server will return this data. So it's like, here is lecture 1, this is the title, this is the link, lecture 2, title, link. The web server uses this data to construct the response, so it has to build the HTML for it. This HTML is sent back to the client as an HTTP response. And finally, the client renders the page to display the actual content. It will put the logo in the right place with the right colors, and the text in the right place and the right colors, and so on and so forth. Questions on this overall structure? All right. So databases, this is what we're going to be focusing on for the next, I think it's 30 or so slides. For this class, again, we're covering SQL databases. SQL stands for Structured Query Language. Some people will say SQL. I prefer SQL just because it's shorter to say. Each database in a server can have a number of tables. So a server can have any number of databases, and a database has a number of tables. Each table has a structure. So if we're thinking, oh, it's a table, say like a spreadsheet, It has columns for each entry. So in this example table, we have a table of bots. Each bot has an ID, each bot has a name, each bot has something that they like, and each bot has an age. The database server acts as the manager for all of this data. It manages how this data is stored. So it wants to make sure the data is stored efficiently on disk and wants to make sure that, say, if there's a power outage, that the data isn't lost forever. The language that is used is SQL. So structured query language is the language that most, well, SQL databases will use in order for you to interact with them. It allows you to query data, so get data from the server, and allows you to modify the data, so change what's stored in the server. This is defined by the International Organization for Standardization, which is ISO, because I think it's French. And it's implemented by many, if not all, SQL servers. Well, it's implemented by all SQL servers. This is a declarative programming language. So if you've taken 61A, you might have learned SQL because it's a different sort of programming paradigm. You're not going to be saying, say, like for loops and if-then statements. You're just going to say what you want in a defined structure. So you're not telling it what to do. You're just telling it what you want. Yeah. The alternative for languages that you've probably used is imperative programming languages, where you just tell it what you want to do. So C, Python, Go, those are all imperative programming languages. All right. We're going to spend the next couple of slides basically just taking a very fast crash course of SQL. You'll definitely have more practice with this in either the next homework or the project. So yeah, and you don't need to, memorize all of SQL, just enough to know how to write exploits and how to read statements. So the first statement that we're going to use is the select statement. Select is used to select columns from a table. So generally this is listed as select something from something. So as an example, if I wanted in this table, I know that bots has name and an age, has a name column and an age column. I can say select name comma age from bots. So in this case, what I'm getting is 2 columns from this table. And in this case, I'm not saying I want to filter any of the rows. So I just want all the rows. So what's returned is this table with just the 2 columns I asked for. It has the name column with evanbot, codabot, and pintabot, and it has the age column. And you'll see it's also returned as a table, but this is sort of a subset of the columns in the full table that I asked for. I can also ask for select star. So instead of a list of column names separated by a comma, I can also just say select star from bots. So in this case, it just says select all columns, and I just get back all of the data in this table. So it's basically someone read every row of this table, put it in a new table, and gave it back to me. There is also a finicky thing you can do with select statements. Here I was saying select column names, or in this case, select all column names. I can also do this thing where I select constants. So select the constant CS and the constant 161 from bots. And what this is going to do is it's going to look up each row in the table. It says, okay, I want the constant CS and I want the constant 161. So what I end up getting is 3 rows, and all of these are oops. Give me 10 seconds to fix this, because yeah. There we go. It's like it never happened. We get 3 rows here. Each row has the same contents. It has CS and 161 because for each row, we just return the constant CS and 161. So it's a little bit finicky, but you might find this useful for the project, just as spoilers. All right, that's how we get data from the database. Now we want to start doing some useful features. Oftentimes we don't want all of the data, we just want all of the data that we care about. So the where statement, or the where clause, lets us filter out certain rows. With the where clause, with the where something, we can use arithmetic comparison. So we can use the classic less than or equals to, greater than or equal to. Equals, something to keep in mind is that it uses 1 equal sign and not 2, or not equals, which is this weird brackets sort of thing. I don't know why, it is what it is. You can use operators. So maybe I want to say age plus ID is less than 5. I don't know why you would want to do that, but it's something that you could do. We also have minus, times, and divide per usual. There are also Boolean operators, so we could say something and something if we want multiple parts of our where clause. And just something to keep in mind is that and takes precedence over or. So if it always evaluates something and something before it evaluates something or something. All right. So in this case, now we're saying select star from bot. So select all columns where the likes column is equal to the string pancakes. So in this case, we return a single row that is just evenbot, because of all of the rows in this database, only one row has likes equal to pancakes. So we end up getting 1 row and 4 columns. We can also do something a little bit fancier. So we can say select name, just the name from bots where the age is less than 2 or the ID is equal to 1. So in this case, we look at this table, we look at each row, we see, okay, for this row, the ID is equal to 1. For this row, the ID is not equal to 1 and the age is not less than 2, so we aren't going to return this row. For this row, we see, oh, the ID is not equal to 1, but the age is less than 2. So what's going to happen is we return just the name, so we still only have 1 column, and now we have just evenbot and pintobot. We can do a lot more complicated and fancy things, but the where statement starts to give us a bit of control over what data is actually returned, and we'll see how this helps us later on. All right, so that's how we select data. There's also some statements that help us to change the data in the database. So the first one we'll talk about is insert into. This is used to add rows into an existing table. Generally, when we use insert into, we're also going to see the word values. This is just shorthand for defining some constant rows and columns. And the only time we really want to do this is when we're constructing new rows to be inserted. So this is you'll generally see them used together. In this case, we have something like insert into items, values, and then this is one row and this is the other row. So you see that different rows are separated with parentheses, and then within the rows, the different columns are separated by commas. In this case, we still have our 3 rows from the original table. And here we're adding 4. We have the name is Willow, who likes catnip, and her is. Willow is the name of a cat that is owned by one of the instructors of this course, but I actually don't know their gender. Willow's favorite thing is catnip, and Luna, ID 5, who likes snaps and whose age is 7. Okay, that's how we insert data. We can also update data. So whereas insert is used to put additional rows into the table, update is used to change existing rows in an existing table. Generally for update, it's going to be update something, set something. This is really the extent of what you're going to see in this course. It's also usually combined with where, because if we don't put where, now we're just going through and updating every single row in the table, and we probably only want to update specific rows. So the full syntax is something like update table, set column equals something. So set column to some value where some condition is true. So in this case, we can say update bot set age equals 6, where name equals Willow. We go through, we check, okay, name is not Willow, so we move on. Codebot, or name is not Willow, move on. Eventually we get to this row here, we see name is equal to Willow, so we've satisfied our where clause, and we say set the age equal to 6. So now we've gone in and updated the data in our database, in our table. All right. Next is the delete clause, or the delete statement. So delete from is used to delete rows in a table. This is also usually combined with where, because if you just say delete from bots, you're going to match every row and delete every row. Sometimes you want to do this. Most of the time, you don't want to delete every row in the database. So the syntax that you'll usually see is delete from something where some condition, and this where clause is the same as before. So in this, in this example, we're saying delete from the table bots where the age is greater than or equal to 6. So we go into this table, we see age is not greater than or equal to 6. Same with CodaBot, same with PintoBot, but now we see row 4 matches because the age is greater than or equal to 6, and row 5 matches because the age is greater than or equal to 6. So we go through, delete these 2 rows, and we're left with our original table with 3 rows and 4 columns. Next, we have the create statement. So in all of this, before we've been assuming the existence of some table, create lets us create a table as a whole. It's also sometimes used to create databases, but we won't worry about that too much in this class. The syntax is create table and then some, for this class, create table and then some schema. So we set in these parentheses, each one of these lines corresponds to a column. We are saying there is a ID column whose data type is int, a name column whose type is varchar, which is really just a string with 220 with a max length of 255, a likes which is also a string, and an age, which is, that's not an int, that should be I think it would technically be decimal, either decimal or double. I don't remember off the top of my head, but because it has non-integer values here, it wouldn't be int. But in this, I guess if we're creating a new table, it's technically fine. In this case, we're creating a table with these 4 columns. So this creates a new table, but its contents are empty right now because we haven't inserted any rows into it. And finally, drop. Drop is used to delete tables and also sometimes databases. The syntax is really just drop table and the name of the table. So if we were to say drop table bots, now this entire table doesn't exist and we're left with only our cats table. Oop, that's a slow fade. All right, questions on the, 6 statements that we went through? All right, we'll sort of see how we can use SQL maliciously more in the future. So maybe that'll hopefully give you more of a chance to work with it then as well. So in SQL, we also have a couple of syntactically relevant characters. If we use 2 dashes, that's used for single line comments. So if you've used 2 slashes in C, that's for a single line comment. Or if you've used the hashtag in Python, that is also used for a single line comment. It makes the rest of the line ignored for the purposes of syntax. Semicolons can be used to separate different statements. So if I had update item set price equals 2 where ID equals 4, I can put a semicolon and then start my next statement. And if I took all of this and executed this all at once, it would treat these as 2 separate statements and execute both of them. This behavior here is a little bit finicky. This says, so first it's updating the item with ID 4 and setting its price equals to 2. And then we're selecting the price from items where ID is equal to 4. So in this case, we're always going to return the value 2, but it's only going to return if there exists a row where the ID is equal to 4. So that's just what you would get with this statement. It's a little bit weird, but it was just what we came up with as an example. As you can probably guess, there's a lot more to SQL than we have taught you in the last 30-something slides, but you're only really responsible for everything that we've told you about in the slides previously. And you shouldn't need to start looking into joins and left joins and right joins and outer joins. If you've taken 618 before, you might be familiar with those, but you're not responsible for them in this class. All right, that is SQL. Now let's talk about how to exploit SQL. So I've written some more Go because as I was making these slides, I was writing Go and I was sort of in the mood for writing more Go at the time. So here's my handler. I've graded out all the parts that you don't need to worry about. The only real important part is that I have some query here. It's constructed from this sprintf call. So this is using a format string, and then it's executing that query. You might have noticed we have this same string manipulation issue. When we were dealing with XSS, we had vulnerabilities because we were inserting text into an HTML template as data or as control, as HTML. And the attacker was able to exploit that by putting in malicious HTML. We have the same idea here, and you'll see how that manifests shortly. But for example, if I were to say get items and then items equals paperclips, then we would end up constructing this query. Item name in this case is paperclip, so we put that into this %s, we get select item and price from items where name equals paperclips. So this looks all right now, but again, we can start to think about how we might exploit this. What if we use an input like get items and the item name is a single quote? What query does this create? Well, if we use this string substitution before, item name is just a single quote in this case, and we put it in, we get select items, comma price from items where name equals quote, quote, quote. What happens when the SQL server tries to execute this? Or what happens when the HTTP server tries to execute this on the SQL server? And or how about this? Is there a syntax error here? All right, I wanted someone to say it. It quotes the next bit of SQL, kind of. Well, the SQL server is going to try to interpret this as a statement, but it's going to notice, that's weird. I have these two quotes here, which make the empty string, but now I have this unterminated string here. What we've actually done is created a syntax error. So if you've ever written SQL and you didn't close your quote, or maybe you put too many quotes in, or maybe you in any language you forgot to close your quote, you've gotten maybe a compile error or a Python error, and it just refused to execute. The same thing is going to happen on the HTTP server. It's going to try to execute this. It gets, oh, the SQL server says you have invalid syntax. The server is going to go, oh no, something's gone wrong. I'm just going to return back, 500 internal server error because something has gone wrong and it can't figure out why. So that's great if we wanted to, create SQL errors, but that's not really malicious. We can try to write payloads that are a little bit more subtle than this. So if we said, let's say, quote space or space, quote one quote equals quote one, and notice we don't have another quote at the end here. When we take this string and we slot it into this name here, we'll get select item price from items where name equals quote quote, so name equals empty string, or quote one quote equals quote one quote. So reading this one more time, this says select item and price as long as either the name is the empty string or the string one is equal to the string one. Well, the string one is always equal to the string one. So we know that this is basically where name equals empty string or true, and we know that anything or true is true. So in fact, what we've done is we've gone through and really just gotten rid of this where clause here, and it's going to return every single item and all of its prices for every item in the database because we were able to exploit this vulnerability here and slot our own input that creates a malicious SQL statement when the string substitution is used. All right, that's maybe it's all right for if we wanted to return a large amount of data. Maybe that we could execute a denial of service by having it return a lot of data, but it's still not malicious. Maybe we can do something like this. We'll say quote, because we still need to get rid of this quote from the original statement, semicolon. So we're ending this first statement now that we're out of the string. Now we say drop table items. When we put this in, we see that this becomes select item price from items where name equals empty string. So there probably aren't any items whose name is empty string. So this statement probably isn't going to do much. And then it's going to do something else. It's going to do a semicolon. So the SQL server sees, oh, it's starting another statement, and we're saying drop table items. Can anyone tell or guess why we have the extra 2 dashes at the end here? as a reminder, the 2 dashes create a comment in SQL. Why might we want to create a comment? Yes, exactly. We're commenting out this quote here, because if we didn't do that, then we'd have drop table items quote, and the SQL server sees that and says, huh, you're not supposed to have a quote there. That's a syntax error. So it's just going to end up not executing anything. But if you do this dash dash, then what you just have is a comment at the end of your thing, and it's going to ignore everything after that dash dash. So what it really sees is just drop table items and then some comment that I can ignore. So now it's going to go through, select nothing from the items table because name equals empty string, and then it's going to delete the table items. You can imagine why, say, as a website owner, you might not want people to do this. Yes, and the quote is just to, or the dash dash is just to comment out the remaining quote. All right. That's the idea of SQL injection as a whole. Are there any questions on any of this? You might be starting to notice that a common theme here is that you should never use string substitution for anything ever. But yeah. All right. So SQL injection is when we can inject SQL into queries constructed by the server that cause malicious behavior. Generally, this is because someone's trying to use string manipulation for SQL queries, and that string manipulation lets attackers just slot in their own syntax thing and have that parsed by the server. This gives the attacker to execute any SQL that they want on that SQL server. So they can maybe drop tables, or maybe they can say create a user for the attacker to log into the server directly, and so on and so forth. Maybe it'll delete all of your customers and then cause you to lose your revenue because now the customers don't have access to your site, and so on and so forth. Yeah, leak data, modify records, delete records in table, basically anything that you could do on the SQL server. So there are a couple examples of how this is exploited in the wild. There were a couple examples that were given in the original version of these slides, but all of them were too old. So we just have a couple of funny comments here. This is an XKCD. We see that the mother named her son Robert, quote, close parenthesis, drop table students, and we have this same structure here. In this case, I guess they're assuming that there's an additional parenthesis. So maybe this is a insert into where you have the values and then the parenthesis. And then we have the semicolon drops table students to create the new statement that deletes the table, and then the dash dash just to get rid of anything that might be following. This is a classic XKCD. If you're not familiar with XKCD, it's really just a set of comics that's very nerdy and has to do with computers and science and other miscellaneous things. Highly recommend it if you aren't familiar with it. I see someone renamed themselves in Zoom chat. There's also this. I'm just going to let it speak for itself. It would be funny if it worked though. All right, so that's SQL injection, but we don't always have like an obvious return, or we don't always get to see the return value of the SQL server in an obvious way. Sometimes we might get that. So if we're getting a list of products, maybe that will happen, but sometimes this is not the case. If we're doing something like password verification, we won't ever get to see the return value of the query. It'll just query the password hash, then hash it, and then return you true or false. For user account creation, it's never going to say, oh, you have created your account, here is a list of random data. It's just going to say account creation successful. So you're not always going to get feedback from the server. Sometimes the best that you'll get is just some sort of true false. So we call this blind SQL injection, where you have little to no feedback from the server. And this makes attacks more annoying, but the vulnerabilities are still exploitable. We don't want to be relying on security through obscurity in that you're obscuring the return values of the SQL server. In addition, we also have automated tools that can detect SQL injection and begin to craft inputs for the vulnerable SQL injection input. So this is less of an issue than it used to be, but it's still kind of annoying. So we won't really be making you do blind SQL injection in the project, but it is something to keep in mind that exists. All right, so this is how we exploit SQL injection. Let's talk a bit about how we can defend against it. So the first one we'll talk about is input sanitization, and you might actually see some commonalities between this and XSS. For input sanitization, we have two options. One, maybe we just disallow special characters. We only allow letters and numbers, and maybe certain punctuation, or maybe the space here or something. But we disallow the quote, we disallow the dash, we disallow anything that could possibly be harmful. We could also escape those characters. So SQL injection relies on certain characters that are interpreted in special ways, but SQL allows special characters to be escaped in order for them to be treated as data. This is all right, and in theory, if you use it correctly, it is secure, but it's difficult to build a good escaper that handles all edge cases. You should never try to build a SQL escaper yourself because you will make a mistake and it will lead to a vulnerability in whatever code you use it in. You should always rely on libraries. So in PHP, there's a function called MySQL real escape string, or it's some combination of those words. Rely on functions that are widely used and trusted if you have to use this option. It's also good as a defense in depth measure. If you have no other option, we'll get into the better option next for the next slide, but it's good to use this if nothing else. As an example of how this would be used in the original code, we just add an extra line here that makes sure that the item name is the escaped version of the original item name. So if this item name has, say, single quotes in it, the SQL escape function will go through and escape every single quote there. And then we can safely slot it into this %s here and then run that query, and it should hopefully be fine, assuming there's nothing wrong with our escaper. A better way to defend against this is something called prepared statements. Generally, you'll see this as a question mark when you're writing SQL statements. So the idea is, instead of trying to escape things and give it and pass it to the SQL interpreter in a way that it won't treat those characters as control characters, the idea is have it fully parse the statement first, and then when it sees the question mark, it'll know, okay, this is something that will be filled in at the end. So only after it has finished parsing the statement, then it will insert the data. So the idea is whenever it sees a question mark, it'll know, all right, parse all of this first. Don't worry about, any data that needs to be put in. And then now I'm going to pass you this data. Don't treat this as anything other than data and just slot it into the syntax tree in the right part. This means that this untrusted input never has the chance to be parsed. So it's only ever going to be treated as data, as a string, or maybe as a number. In this, again, in the Go code, you'll just see it like this. So db.queryRow can take additional parameters. And we see we have select name price from items where name equals question mark. And this whole string, this literally has a question mark in it. And then when it's passed to this function, it'll know, all right, the next parameter is for this question mark here. So it's similar to printf, except it's used for SQL. And this is actually the best way to do it. The main issue with this is that this is not actually part of SQL. There is no part of the ISO SQL spec. There is no part of basically anything that says that prepared statements need to exist. Instead, it depends on the SQL driver. So if you're using a library to interact with the SQL server, it's up to that library to provide prepared statements for you. So yeah, and then you have to rely on the API in order to actually convert that prepared statement into the protocol that your server uses. So MySQL uses one protocol, Postgres uses another protocol, and so on and so forth. There's no standardized way to do this. So again, you want to be thinking about consider human factors. Why wasn't this a part of the original SQL spec? I can only assume it was because they didn't intend SQL to be used like this, where you're programmatically constructing it from untrusted input. But again, consider human factors. All right, questions on SQL injection defenses or SQL injection as a whole? All right, well, we, I think, are right on schedule. So why don't we take a 5-minute break? We'll come back at 4:26. And yeah, I'll see you guys all then. So that was SQL injection. That has to do with the language SQL, but we can generalize this to other problems. This sort of leads into a general class of attacks as a whole as command injection. So with command injection, we're using untrusted data. Well, I guess in SQL injection, we're using untrusted data and we're treating it incorrectly. And that's not just a SQL specific problem. This can happen in other languages. So the example that you might have seen if you've ever worked in C before is the system function. The system function takes in an entire string and it spawns a shell and executes that string inside the shell. So it's basically like someone took your string, copied it, opened a terminal, put it in your terminal, and pasted it. This creates issues if you don't write your code correctly. This is some C code. This isn't in Go for reasons we'll see shortly. This is some C code, and in theory, it just finds an employee from a phone book. So we have an input sequence of characters. We have a output command buffer, and we're just going to use this snprintf function that will take this format string and write the resulting output of that format string to this command buffer. So we see we have this %s here. We take the regex and we put it into this %s. So for example, and yes, again, here is string manipulation. If the regex value is Weaver, who is one of the instructors of this course, we'll get grep Weaver from phonebook.txt. This will go through phonebook.txt, execute the regex, which in this case is just the string Weaver, and return all of the results. Well, what if we again did something finicky? Instead of, say, Weaver, we'll do quote semicolon, because we can do semicolons in Bash as well. Then we're mailing to mallory@evil.com the contents of that C password. This is all shell stuff. Maybe you're familiar with it from Project 1, but if it's not, that's totally fine. And then at the end here, we have an extra command just to make sure that our command is well-formed as a whole. We see that the resulting command is grep empty string. So this will actually error out because it doesn't have enough parameters. Then we're going to mail to Mallory the contents of that C password. And this is an entire command. And this one is well-formed. And then we see we just have a touch command that touches the empty string and the phonebook.txt. Touch will really just not do anything with this, so it doesn't really matter. And we can see that this has come about as from the same issue. We have the string replacement and we're using it for something that can be very powerful. We're giving the attacker the ability to write control characters and inject their own commands into this string. That's why it's called command injection. The way we defend against this in general is pretty much the same as in SQL injection. You could try to sanitize your input, but this is hard to implement. It's difficult to get 100% correct. And for the general case of command injection, say we're working with shells, you have to deal with a lot of different possible shells. There's bash, there's dash, there's dash. They all end with sh because shell. And each of these will handle strings slightly differently. So it's hard to get correct. A better way to defend against this is to use safe APIs. So before we were using this system command, but if you remember the KISS principle, which we talked about, I think all the way back in lecture 1, it's keep it simple, stupid. For system, we're executing an entire shell, say bash, just to execute a single command. And this is too much power. We're giving too much power to the program to do malicious things if it receives malicious input. Instead, we would want to use something like the exec_feed function. This will directly execute the program, like without going through a shell, and it won't parse any of its arguments. So most programming languages have these safe APIs, and you should pretty much always use them instead of using, say, system, or we'll go through the other unsafe functions. So for C, we have system, which runs a shell to run a command, and execv, which runs a program directly with the arguments that you specify one by one. Python has os.system, which is unsafe, and it has subprocess.run, which is a similar idea as execv in Python. In Go, it actually only has one real command for this, and it's exec.command. And you'll notice there is no unsafe version of this code. Go actually doesn't have, well, at least not an easy way for you to mess up and write unsafe code. So again, consider human factors. If you're going to provide two alternatives to the user and one of them is easier to use, say the system call, they're probably going to go with that one. So Go doesn't let you do this. Go only lets you use the safe version. All right, that's command injection. So like yesterday, we had one half of the lecture that was super technical. Today, we also had our SQL injection and command injection, which is all super technical. And now we're going to talk about something a little bit more, or a little less technical. This one's more technical than UI attacks, but you know, we basically needed to shuffle these lectures around to make sure they all fit in approximately an hour and a half. So for CAPTCHAs, the idea that we're working with here is that when we're writing a website, we want humans to interact with our website. If I'm writing a website, I don't want it to be overtaken by bots posting spam comments and whatnot. So most websites are designed for human usage. For example, a login page, we want the user to type in their password. We don't want an attacker to write a program that automatically tries 10,000 different passwords to see if any of them let you log in. We need some way of stopping the computer from interacting while allowing the human. If you allow robots, this can lead to certain attacks. So a denial of service might just launch a million requests at your website at the same time, and this will overload it, cause it to go down, and suddenly your users can't access your website. We'll talk about this more in the networking unit, which begins tomorrow. They might also just have spam. So if you have been on, say, YouTube videos with spam comments, or pretty much anywhere on the internet, there's always going to be spam. Generally, those are bots masquerading as users and just posting links to a very wide area. The defense that we have in place here is something called CAPTCHAs. So CAPTCHAs are a challenge that's easy for a human to solve, but hard for a computer to solve. This is technically stands for a completely automated public Turing test to tell computers and humans apart. I'm sure whoever came up with this felt really clever, so yeah. It's also sometimes called a reverse Turing test because a Turing test is supposed to be easy for computers but hard for humans, and a reverse Turing test is the exact opposite. We use CAPTCHAs in order to distinguish web requests from humans and web requests made by robots. And the general usage for CAPTCHAs is present a CAPTCHA to the user. If the CAPTCHA passes, assume that the user is human. If the CAPTCHA fails, assume that the user is a bot, and then don't allow the request. So these are some examples. You've definitely seen these before because these are everywhere on the internet. Maybe not these ones specifically, but you might have seen newer versions of these. Not both of these, but a large proportion of CAPTCHAs rely on just reading distorted text. So right now we're assuming that it's hard for a computer to read a CAPTCHA and be able to tell what's being said here. Like I can tell that it says JITNEYS, but that would be hard for a computer to do because it's so distorted and computers aren't great at this sort of thing, although they've been getting better in recent years. And we'll talk about that shortly. Actually, I don't know if we'll talk about it shortly, but we might. It might also rely on identifying images. So computer vision has always been a hard problem for computers, and I think we're only just now starting to get the hang of it. But for something like this, we're assuming that it's hard for a computer to tell the difference between cats and dogs in this photo, even though I can easily see, here's a cat, here's a cat, here's a cat. I think that's it, maybe. Or I don't know, maybe I'm a computer. Other examples are audio clips. So audio processing is also kind of hard for computers if you've ever used something like Siri. So we're assuming that humans can easily listen to audio and hear what the words being spoken are. In more recent years, we've also seen a lot of machine learning related CAPTCHAs. A great thing about CAPTCHAs is that you have a lot of humans doing things because you told them to. So what we can put this towards machine learning. Machine learning often needs a lot of data that's like, oh, this is a dog, this is a cat, or say this is a motorcycle and this is a stop sign. And you have to feed all of this data into the algorithm, but someone needs to be there to classify the data. And a lot of CAPTCHAs are used for that purpose of letting humans classify data for us while they solve these CAPTCHAs in order to be let into their website that they want to use. So this basically crowdsources the cognitive power of humans who want to use websites to create these large data sets that can then be fed into the algorithms, into the machine learning. If you've seen a lot of car-related CAPTCHAs lately, say motorcycles or buses or stop signs, maybe that's because some people are working on algorithms for, say, a self-driving car. This is another XKCD. I will just leave it up here for a moment. But yeah, the main takeaway is really just that CAPTCHAs, main takeaway for this at least, are that CAPTCHAs are largely used to train machine learning algorithms. So you can always tell what, say, Google is working on if you complete one of their CAPTCHAs. There are some issues with this. So CAPTCHAs have always been an arms race because computer algorithms are getting better and better at doing things that we thought only humans can do. And this means that the CAPTCHAs need to get harder. There's also an accessibility issue here where harder CAPTCHAs are hard even for humans. And I'll show some examples on this side in a moment. But there's also ambiguity. CAPTCHAs might be so hard that even the person trying to validate your CAPTCHA doesn't know the solution. Maybe some algorithm is generating these CAPTCHA data sets, and then the validator also has to figure out which one is the real one on its own, but even it can't figure it out. So it's like, at this point, what are you really verifying? The final issue is that not all bots are bad. Sometimes there are bots that go around the internet that we want to let through. CAPTCHAs can distinguish any bots from humans, but it can't distinguish the intent of bots. So there's no CAPTCHA algorithm that can let in a good bot, but not let in a bad bot, because all bots are really just algorithms. And if someone creates an algorithm that good bots can use to, say, solve a CAPTCHA, the bad bots can just use them as well. So there's no way to distinguish the intent of bots. One example of good bots is crawlers. So for search engines, these have to use bots to scour the internet and index every single piece of text. But if your website has a CAPTCHA in front of it, that your bot might not be able to index that website, and then that website doesn't get as much traffic as it would otherwise because it's not on the search engine. So there are trade-offs with CAPTCHAs, and there are major issues with this. These are CAPTCHAs that have existed. Some of these are jokes, but I'm actually not sure which ones are which, but I've been told not all of them are. I don't want to try to do this. That's not even English. I don't know. And half of these are Greek letters, so I'm not sure. There are also attacks on CAPTCHAs. CAPTCHAs only really verify that there's a human in the loop, but it doesn't stop bots from filling everything else out in the form and then just presenting the CAPTCHA to the human, telling it to solve it, and then submitting the form. So we can actually outsource CAPTCHA solving to large workhouses, usually in foreign countries. They usually cost as little as a few cents per CAPTCHA. So I could have, I guess, depending on your threat model, tens of thousands to millions of CAPTCHA solved just by paying, say, $100,000, which might be feasible for the adversary that you're defending against. The result of this is that CAPTCHAs more or less end up distinguishing the attackers who are willing to spend money from the attackers who aren't. And this is not necessarily a bad thing. If you think all the way back to lecture 1, security is economics. You can install a CAPTCHA to make the cost for the attacker higher, and that will stop some attackers, but if the attacker has more to gain than they will lose by spending money on, in this case, CAPTCHA solving services, then they will still conduct their attack. So if you go and search CAPTCHA solving, you'll find tons of CAPTCHA solving services, all of which are fairly cheap, again, depending on your threat model. So yeah, these exist. And that actually brings us to the end. So we are about 15 minutes early, at least we will be by the end of the summary. Just to summarize, we have SQL injection. We talked about how web servers work. So they use SQL databases to store their data and use the SQL language to interact with those databases. When we use untrusted input from the user as SQL, that is to be parsed, that creates a SQL injection attack where the attacker can construct their own queries by injecting specifically crafted payloads into the command that is run on the server. SQL injection might also be blind if you get little to no feedback from the SQL query. And some defense that we talked about are input sanitization, where we escape the special characters, or prepared statements, where we actually parse the entire SQL query first, then insert our data afterwards. And this is the only foolproof way of doing it. Command injection is really just the generalization of this. If you use untrusted input as any language that is to be parsed, you could have the potential for a command injection vulnerability there. So what you really want to do is keep it simple and use safe API calls. Use execv instead of system and so on and so forth. CAPTCHAs are ways for us to tell computers and humans apart for something like a website. It's easy for a human, but it's difficult for a computer. So if you're trying to read distorted text or trying to identify images, we're assuming that humans do this easily, whereas bots don't. The original purpose was to distinguish humans and bots, but nowadays it really just forces the attacker to spend some money on CAPTCHA solving services. And it also provides really large data sets for machine learning algorithms. Some issues with CAPTCHAs are that CAPTCHAs are getting harder and harder because computers are getting smarter and smarter. And at this point, computers are becoming so smart that sometimes computers can read CAPTCHAs better than humans can. There's also ambiguities that CAPTCHAs might be so hard that the validator doesn't even know the solution to itself, so it becomes difficult to even use CAPTCHAs because at this point it's just complete gibberish. Not all bots are bad, so sometimes we want to let bots in to our website, but there's no way for a CAPTCHA to distinguish the intent of a bot. There's no way to tell between a good bot and a bad bot. There's a question, how do the machine learning trainer CAPTCHAs check if you're a human? So generally what it's going to rely upon is the general consensus. So the assumption is if you give out 10,000 CAPTCHAs and say 5,000, say 9,000 of them get the answer correct and 1,000 of them get the answer wrong, you're assuming that that 9,000 is the correct answer. And it's also going to have measures in place. So it has a set of images that it already knows. So it'll actually present you with an image that it knows the answer to, and also an image that it might not necessarily know the answer to. So the first one validates that you're actually human. The second one helps give training data. And so if you get the first one right, the assumption is you're going to get the second one right. And then sort of it becomes an ongoing cycle of now it presents you one that it knows and one that it doesn't know. And then you have to solve both in order to get in, and then it's assuming you're solving both correctly. And then it will rely on the consensus of, say, millions of CAPTCHA users, like some services, some CAPTCHA services. Does that make sense? Yeah. All right. Very good question. Any other questions? All right, that brings us to both the end of this lecture and the end of the web unit. So you now technically have everything you need to do project 3, but I'd recommend focusing on project 2 first because project 3 is not out. But yeah, I will see you all tomorrow.